That's not... See, this is why I don't always trust things on YouTube. Hi. Today we're going to, well, we're going to talk about a lot. I've got some videos and I've got a bit of a bone to pick with YouTube. But as usual, let's just watch. Let's take any notes you have. I'm going to make this a little bit larger. Dangerous, they say. I'll give you what information I can while we're recording. But, I mean, just watch. So first off, I'll preface this by saying they call it hot ice. So if you want to look up how to do this, if this is running a little bit quickly for you, you can go there, or obviously there's a link down there for you to follow. This is one you could totally do at home with being careful. That wasn't clear at all. Right. As far as I know, this is real time. You can see those bubbles coming off the stick. This is not sped up. This is not a time lapse. So that's interesting. Some of you may know about what's the word? Super cooled water. Obviously, that's not the case, and I'm gonna tell you why in a bit. No, I'm not following. No, no, I'm not following the suggestion. You know when they said don't try it at home and go with supervision? If this is making anyone uncomfortable, I'm sorry. Oh, they're not even going to show the hand coming out? Oh, that's rough. I have several bones to pick, but let's start here. First off, they call it hot ice, all right? So first, I'm looking at this. This is a chemical reaction. I see bubbles, right? There's things happening here. I don't like this color. They mention vinegar. They mention baking soda. There is water being mentioned too. They do say to add some more water, but I think it's worth saying what they have here. They said leave it for an hour. What they have here is there's also some water there. I think these crystals, when they scooped it, it was powdery, but we are adding more water. So there is that. Now, if we're going to make hot ice, I guess you need water. I mean, we learned that dry ice wasn't made of like H2O. Maybe they're suggesting it's a different compound, except you just added water and you made a mixture. I think it's important to point out we have here this solution. This looks clear, colorless. I mean, it's not really, I don't know if I'd drink it because, like, if your water comes out of your sink like that, I don't know, I'd suggest getting a filter. But then we have this. And so, in reference to what we've seen before, these crystals were growing out in all directions. And by the end, it was filling up most of the container. But there is still water there. And that's the main thing I want to point out here. If this was hot ice, if it was ice, it would be a complete transition, I would imagine, from the liquid to the solid phase. And this isn't. There is still water present. So to put this in a bit of a lens from what we learned already, I wanted to go through these images. We learned about a saturation test. One of the things that we said was the best way to test if a solution was saturated or not was to add a little bit more solute. And if you added more solute and it dissolved, that would be proof of an unsaturated solution. And if you added more solute and it didn't, that would be proof of a saturated solution. But you'll notice that the amount of solute added is roughly equivalent to the amount that's undissolved. So what we had in this video that made no sense was that we were adding a stick that was, they scraped up a little bit of the solute, but then the amount of solute that appeared way larger. Something else I should mention about this, these crystals, I want to go back. These crystals, that's not what ice looks like. Water makes a hexagonal pattern. That's why snowflakes are hexagons. These crystals are all these long, thin tendrils. This isn't even water that's being formed here. I hate when people misrepresent science. Anyway, to relate this back to what we had seen, here's some other images to show that might illustrate a little bit more clearly than these pictures. We have here 30 grams of sodium chloride and 40 grams we're adding to 100 milliliters of water. In one case, it completely dissolves, so that gives you an unsaturated solution. And here we've got a little bit undissolved, and it's saturated. But again, you'll see that the amount present from beginning is a lot greater than what's left in the bottom of the container. So it almost seems like we're getting something for nothing here. This would be like the video you saw would be like if you added 40 grams of sodium chloride and somehow 50 grams was in the bottom of the container. Where did the other 10 come from? To get a little bit of a clearer picture of how all this works, I want to talk about the term solubility. Solubility has two definitions, one we've seen before and one we haven't. The first one is more in reference to table F, which we've worked with before. You'll notice down here it says that this insoluble really just means has a very low solubility in water, and saying very low, that quantification really gets us to our second definition of how much. So we're not talking so much about solubility through the lens of whether or not it dissolves. All we're talking about today is the how much portion. And the how much is a little bit more complicated to talk about. That's table F we've seen before. This is table G, so you do have this at your disposal, but we should probably take some time to talk about it. Specifically, how much of a solute dissolves in a given amount of solvent at a certain set of conditions. So for this table, we're zooming in a bit, we've got temperature at the bottom, that's our condition. And then over here we have solubility measured in grams of solute per 100 grams of water. So this table is in line with that second definition of solubility because we have a given amount of solvent. We can talk about individual solutes. Each line is its own solute. And then we have a set of conditions at the bottom, namely the temperature. To refer back to what we saw here, in our original image, we have 30 grams of sodium chloride we're adding to 100 milliliters of water. Over here it says 100 grams, but since the density of water is 1 gram per milliliter, 100 milliliters is equal to 100 grams of water. Now, coming over here, this would not be 100 grams of solution. This would obviously be 130 because we have 100 plus 30. So it's also clear that the density of a solution changes, but we're not worrying too much about that. If you want a larger table G to look at, of course, you have the link to the periodic table above my head, the reference tables. When you added 40 grams, we ended up with 4 left over. That means that we have 36 grams dissolved. So now let's take this back over to our table G and see how this works out. 36 grams would be somewhere around here in this area. So here's our sodium chloride. Let me highlight this just to make it super clear. That's our sodium chloride line. You can see it doesn't really change very much. But that's the amounts we're dealing with. So let's take a look. It doesn't give us a temperature, but in terms of sodium chloride, we can kind of guess a temperature. We must be pretty close to room temperature because it's on that lower end, closer to 35. I'm going to say we're probably at 20 Celsius. But what we can see here is if we're dissolving 36 grams, that would be on the y-axis, roughly here. And then we would read a temperature. Let's just say it's 20 degrees for the sake of argument, and that's our solubility. Now, if we had talked about our first sample with the 30 grams, that would be somewhere down here. So I can assume that if the situation that we're describing is underneath the line on the solubility graph, this would be the region where you see unsaturated solutions. Saturated solutions must be what this line represents. Solubility is the point of saturation, probably worth writing down. Specifically, it says there's 4 grams left over. Technically, 40 would be above this line here, but that's not a situation that we're describing because the amount of solute that's dissolved isn't 40, it's 36. So you don't really have any solutions that exist above the line, and then so on the line, that's where we're going to say saturated solutions exist. So that's just in reference to sodium chloride. Of course, there are some other substances to deal with. So let's pick this apart a little bit. I'm going to grab my highlighter again, and I want to specifically point out, because it appears to me that there are two kinds of lines. There are lines with positive slopes, which would imply that at high temperatures, the amount of solute that you can fit in your given amount of solvent increases, otherwise said, as temperature goes up, solubility goes up. And then there are the lines with the negative slope, the downward sloping lines. These would suggest the opposite. For these examples, there's an inverse relationship between the amount that can fit and the temperature. Just to point out that these exist, you can go back and look at them as you need to, but I did make the point of separating the sets of solutes for you. I don't know if you see any patterns here, but here's what I see. A lot of ions. I see metals, sodium, potassium, ammonium is an ion. These are all ionic compounds, and more specifically, they're ionic solids. These substances here are covalent, and I think at the conditions we're talking about, they're gases. So it seems to me that for solids, as temperature increases, solubility increases, but for gases, as temperature increases, solubility decreases. One of the applications we see for this is if you've ever done any canning before, a lot of times to make that good seal, you put the seal on the mason jar and then you put it in boiling water. Yes, that helps sterilize your jam or whatever you're making, but it also does make sure that you're pushing out a little bit of gas so that when it cools back down, you've made a vacuum, which again helps protect the food that's in there. This is only half the story, of course, because things like SodaStream exist, so we should probably also mention that. So we know that at higher temperatures, solids are more soluble and gases are less soluble, but SodaStreams don't work on that premise. They work on pressure. So the way the SodaStream works is that it pushes gas into your container. This creates a higher pressure. If you've ever tried to squeeze a soda can or a soda bottle that hasn't been opened yet, you'll feel that pressure. The container pushes back out as you try and squeeze. But this only works for gases. Remember that gases have that variable volume. And so that you can play around with the space between the particles. Solids don't work that way. So pressure does not have an impact on the solubility of solids. So we have this condition where solids are most soluble at high temperature, gases are most soluble at low temperature and high pressure, which is kind of the opposite of how they behave ideally. So those two, that's how I remember that. They're kind of opposites of each other. Now that we've established what information is on the solubility curve, we do have to talk about how we interpret the information on the solubility curve. So we're going to make a saturated solution of ammonium chloride, that's right here, at 80 degrees Celsius. So we're at this point. Observational evidence, well, if we had our beaker, you should see undissolved solute at the bottom. That's not to say that the solute's floating, I'm just having a hard time drawing it. As the solution gets cooled down, we're going to move this way. Now remember how I said we can't exist in this area above. So what's going to happen is we're going to ride this curve. This curve is showing how much solute can dissolve and is dissolved at various conditions. So if we stopped off at 30 degrees Celsius, we're going to be right here, but we also started off with this much solute up here. So what we're going to see is that as the solution gets cooled down, crystallization occurs, precipitation occurs, and you get more undissolved solute in the bottom of your container. Well, how much? If the original solution is made with 100 grams of water, we can just take the data from the table. I'm going to assume, within reason, that we started off with about 67 grams of solute, and at this point here, we've probably got about 42. So I would expect to see that if you had a perfectly saturated solution, perfectly saturated, I mean, yes, if we had a couple undissolved crystals, this number would be different, but the saturation going down will tell us how many grams we'd expect to precipitate. In this solution, there is still undissolved solute in the upper portion of the solution, but I would expect that cooling from 80 to 30, you'd see 25 grams of solute. So if we had 25 grams precipitate out going from 80 to 30, for 100 grams, if that's a 200 gram solution, if there's twice as much water, solubility scales linearly. That means all of our numbers get doubled, and you would expect to see 50 grams precipitate. This all scales linearly. With 300 grams, you triple, and so on. To get a full appreciation of the previous video we watched and what happened there with those crystals that came out of seemingly nowhere, I thought it would be a good idea to take a look at a different scenario where something very similar is done, but with different outcomes. I mean, rock candy, right? So it's sugar. Yeah, well, there you go. This is a nice one because they outline everything you need. You need adult supervision. Also, 3 cups of water. Go for it. 3 cups of sugar. Geez, 1 cup of water. Oh, this is a scenario, right? 3 cups of sugar and 1 cup of water, where the solute is still the sugar, but there's definitely way more of it. That's why it's a bit of a misconception that the solute is the one there in lower quantities, because the sugar is definitely getting dissolved by the salt or the water. That is. Also microwave for several minutes. Definitely gloves. My understanding is this is a precursor to making, candy and caramel too. Fun experience. It's really hard to make sure you don't burn it though. So in the other one we had the stick, right, where you scraped a little bit of the salt, and so we're still changing temperature, but I think this is the big difference. Kind of looks gross, but kind of looks delicious too. Oh, that looks good. Good crystals. Well, yes, that's the question. Like I said, the big difference here is that this stick was added well after cooling, and it says in the cooled solution here, but this one it seems like we're being far less careful with our solution in that we're dropping in the string and we're kind of leaving it there. So that's already a big difference. Obviously, too, here it's sugar, and I didn't really go through this, but the reaction of vinegar and baking soda makes a solution of sodium acetate. That's another thing to consider. We saw table G with a lot of different substances. The idea is that, yes, you can talk about saturation levels with respect to temperature. You can talk about saturation levels with respect to amount of solvent, but also the nature of the solutes is very important in what you end up observing. And so the big difference between these two solutions is that this one, the crystallization occurred over time, and this one, the crystallization occurred pretty instantaneously. So in reference to table G, like what we were seeing before with our ammonium chloride example, we're cooling down this curve slowly. The crystallization is happening over time. That's the example with the rock candy. For what we're seeing with the stick and the sodium acetate, we're cooling down the solution, but we're letting all of the crystallization happen at once. Now, I know what you might be thinking. We said that the areas up here above do not exist. Well, technically they do. You can make, as long as you are careful about it, you can make an unstable condition where you kind of fit too much solute into your solution. This is usually done by finding a solute with a very steep curve. The sodium nitrate and the potassium nitrate are good examples. Cooling slowly with a cover like we saw in the video, but you also have to play around with the temperature, make sure you heat it, and it's very clear. You need a clean container, but it is possible if you can get it fully dissolved. Regions above these saturation lines are called supersaturated. And these are, like I said, unstable. Sometimes you shake them and something falls apart. And what I did want to mention is there's this word nucleation. It's the process of crystallization taking place. And when you have these supersaturated solutions, the instability, it sits as long as it's not disturbed. Disturbance would occur with these nucleation sites. Basically, if small crystals or areas that are crystal shaped are introduced to your solution, then the crystallization occurs rapidly and you crash all the way back down until you have a saturated solution again. You don't crash below the line, but you crash to the line. And so we saw in the video this was done by scraping up a bit of a sample and dipping it in, but you can also use a fingerprint. Is very rough and might have a good couple of areas for that to happen. This one is supposed to play and it's not. All you have to do is pour. Hang on. All you have to do is pour a supersaturated solution, and that the act of pouring when the solution hits a surface can agitate enough for 2 ions to just bounce into each other. And if 2 ions bounce into each other and they stick, that would then be a nucleation site. A crystal has started and then it will just go wild like you saw in the video. But if you stick your hand into a supersaturated solution, that will happen, which I just want to say, don't do that because there is another component to chemistry we haven't spoken about yet, and it's heat and temperature. It is definitely, it puts the hot in hot ice. I don't know if you've ever seen Rookie of the Year. Worth a watch. But there is a good amount of heat transfer involved in this process, and though the person in the bottom is not really showing it, and the person on the top is over showing it, it's not that extreme, but it is borderline uncomfortable. Thanks for watching.